Dr. Sourav Kundu is a postdoctoral fellow at CERN working in the ALICE experiment. And Sourav did his PhD at NISER with Professor Vedanga Das Mohanty. So he will be teaching you root and analysis framework in this school. Thanks, Sourav, for accepting from CERN. So Sourav, you may take over now.
Thanks, Siddharth, for the introduction, and thanks to the organizer for inviting me for these topics. So I will basically talk about root and analysis framework. So it itself a very vast topic, but I will try to give some basic idea. And I hope at the end of this lectures, we will have some confidence to write our own analysis task and do it in the ALICE framework. So for these lectures, I have assigned 4 days and 2 days for the hands-on experience. So in the most of the lectures, I will mainly focus on the analysis framework in ALICE. So today I will discuss about root, where I will discuss mainly about few root objects which are widely used in our analysis. That's the histogram, graph, function and fitting, file and tree. And in upcoming days, I will talk about how to write analysis task in ALICE physics framework from the scratch. Then I will talk about the event properties like pile-up projection, centrality estimation, and how to select those event properties in our analysis task. Then I will talk about the track properties and their selection in the analysis task. And in the last 2 days, in hands-on experience, I will we will do some analysis using some route and try to submit some job in the using the ALICE physics framework. And if time permits, so in last one of the days, I will talk. If I will give a brief overview of the O-square analysis framework, because for the run 3 data and onwards, we are going to use this O-square framework for our analysis. So let's start with root. So root is a large object-oriented framework for the the data analysis. This root project was started in January 1995, and the first version was released in November 1995. This project was is developed as a collaboration between full-time developers, part-time developers, as also by the users who gives feedback, comments, and other things like fixing of bugs, etc. For full-time developers, we have 7 full-time developers at CHAN and 2 full-time developers at Fermilab, and a large number of part-time contributor, almost around 160, and a large number of users who give this feedback and comments according to which the route is developed day by day. So it's an open source project, and it's available under the LGPL license and used almost by all the major heavy and physics experiment in the world. Now let's see how why this route is very important in our ALICE experiment. So this root object has been used in the ALICE experiment from the raw data taking to our final analysis step. So for example, this raw data from the experiment is packed in various type of root objects, and experimental parameters and calibration results. Those are mainly stored in offline condition database, or the OCDB as a T files, which is a root object. Then the reconstruction, we do our reconstruction and transform this raw data in event summary data, or the ESD, and stored it as in a TTrees, which is also a root object. Then we filtered this ESD data to the analysis oriented data, or the AODs, where we also stored the information in TTrees. Then we use task our analysis task to run over these ESD and AOD TTrees and get the output in terms of various root object like TH1D, which is the one-dimensional histogram, TH2D, two-dimensional histogram, and T3. So we can see that in every step of our analysis, we need this root. So in this lecture today, I will give you the some basic idea about the root. So here I quoted some reference for the root. For the main page, one can get a brief idea about the root from here, and the class reference for the different type of objects of root one can look at here. Correspond So root is a framework written on the C++ language, which and for the C++ tutorial one can look at here, and some hands-on tutorial one can look at here. The root version one can download from this link and install, and for the discussion and queries one can also post their queries in the root forum. So now I assume that most of the participants are familiar with the C++ thing. So I will not go to the C++. I will directly start from the root. So when you after installing the root, one can directly start the root session from their terminal by just typing this root -l, and they can end the session by typing this .q. And one can execute their C++ macro in this root framework using this command root -l and this macro, that's analysis.c or any name. Just to remember that if one execute this root macro with this name, they also need to put this name also in their main program. And the C++ interpreter for the root is the CINT and CLink, where CINT is the interpreter for the root 5, where this the CLink is the interpreter for the root 6. Now there are several commands that one can use in the that one can use during the analysis, like and that can be done with this dot. For example, in order to load the load your analysis macro, if you need to first go to the root environment, then you need to use this .l, which corresponding to the load, and the .l and your analysis macro. And then to execute, one need to do this .x and the analysis macro. Now there are also several shell commands like for which one need to take this dot and exclamatory sign, and for to such example here I have given that the /host name. By typing this, one can found the host name, and the who am I. If you type this in the root environment, you can find the username. So with this basic idea about of the root, let's now move on the selected root objects, which I will going to discuss today, which are basically mostly widely used in our data analysis. So first is the histogram. So what is this histogram? So this histogram is basically a distribution of a variable, or the frequency distribution of a variable. So in the x-axis, maybe you have some variable, let's say x, and then y-axis of the histogram, you will get the frequency for those for the value of this x. That means how many times of your experiment this x has been occurred. So this histogram can be construct using this th1d object. So here I have construct a histogram that is the h1, and one can see that this in order to construct that, we can write the th1d star h1. So the star basically gives you a pointer of this histogram, and you can define the histogram like this way, where this hist name is basically it's the argument to give the name of the histogram, and the second argument is basically gives you the title of the histogram. Then you have another three argument. One is the number of bean x, that means how many beans you want in the x-axis, and this mean x and max x correspond to the range of the histogram. So this definition will gives you a histogram with the same bin width for the every bin. So the bin width is basically the max x minus min x by the number of bin x. Now in experiment, we often needs to define histogram with variable bin width, and we can also do that. To define the variable bin width, we can do it like this, where the first and second argument is the same as the previous one. The third argument is the number of bean, and the fourth argument is the bean is basically an array of a double number which contains the range of the each bean. For example, here this bean is 0, 1. Here I define like this. So here basically you will, if you put it here, you will basically have uh, 1, 2, 3, 4, 5, 6 bin, which have, and the first bin have a range from 0 to 1, then the second bin have a range from 1 to 5, then the third bin have a range from 5 to 10, and so on. Root also allow us to define the higher dimensional histogram like TH2D, which is the two-dimensional histogram, and TH3D, which is the three-dimensional histogram. For example, one can define the two-dimensional histogram like this, similar to the TH1D, where you need to you have additional three argument, so that corresponds to the bin number and the range of the your axis in the y-axis, and this is the same like TH1D, and this corresponds to the bin number and the range on the x-axis. Now, this one-dimensional histogram and the two-dimensional histogram, they allowed to us several operation. Like you can fill the histogram by just calling this fill, and you can fill with it with some weight. Like here, if you want to fill some value, then the value will be go with some weight, and for the weight you can put it in the second argument. You can draw the histogram, you can scale it, and you can also add two histogram. Like here is the two histogram H1 and H2, and you can add it by using this add command. You can also divide two histogram. You can set the range of the histogram axis. You can set the range of the histogram axis and set the minimum and maximum range of the histogram axis in the y-axis. You can also rebin, that means you can also merge two bin of the histogram, and you can also read the histogram and what is the bin content or the numbers of the occurrence of value x in a given bin. You can do it by just doing get bin content, and in argument you need to put the bin number, and you can also find a bin find the bin number for a value of the x-axis. For example, in x-axis, if you have some value 5 or 4, you can find that this 4 and 5 belongs to which bin. You can do it with the h1 find bin. There are other several members for this th1d function, and you can find it if you go here in this link. Now root also allow us to book a histogram more than 3 dimension, and for that we use the THnSparse. So in THnSparse, one can use how many axes they want. For example, here I give an example of a THnSparse where I define a THnSparse which have a 8 dimension. So how to define this THnSparse? You can define it with this function, with this object THnSparse. So here I have written that. So the first argument corresponds to the name of the THnSparse, and the second argument is the title, similar to the histogram. And this the first argument corresponds to the number of axes that you want to put in your THnSparse. For example, it is 8 defined here. Then you have the beans xmin and xmax. So those are the those are basically the doubles values. So these beans basically gives you the number of beans in each of those axes, which is defined here. For example, now for the first axis we have 10 beans, for the second axis we have 10, for the third axis we have 5, for the fourth axis we have 30, and so on. And this x min and x max corresponds to the range of those axes. which is also a double value, which is defined here. Now you can also fill this THnSparse using this fill, and in argument you need to give a uh, double value, that is the x. So this double value is basically the n dimensional value. So for example, here is a eight dimensional array, and in each of the position corresponds to the value of this each of the variable of this axis. Now one can project this THnSparse in one dimensional, two dimensional array using this projection operator. So if one wants to do a projection in the one dimensional, one can just write the HS projection, and in argument one needs to give this x dim. So this x dimension is corresponds to the axis number, means the which axis you want to project. For example, if you want to project the first axis, you need to give 1. If you want to project the third axis, you need to give 3, and so on. And one can also project it in two dimensional by giving two array. The first array corresponds to uh, giving the two argument, and the first argument corresponds to the number of the x-axis, and the second argument corresponds to a number of the y-axis. For example, if one puts 2, 3, then he will project a two-dimensional histogram from this THnSparse, where the x-axis is basically the second axis from the THnSparse, and the y-axis would be the third from the THnSparse. And one can also project in particular range of the histogram by setting the range of the axis. So if you set the range of the, for example, the first axis by taking by just getting the axis first axis, then set the range between some value low and high, and if then you can and after that if you project, then you will just project the first axis with in this range, low and high. Now let's move to the graph. It's also a very useful object that we use in our analysis. So in contrast to the histogram, where in the y-axis we have the frequency or the number of occurrences, here this graph means you have a particular value of y correspond to a particular value of x, and root has offered as a various type of graph like t-graph error, where you have the error on the data point, t-graph asymmetric error, where you can have the asymmetric error on the data point. For example, in the you can have a different value of the error in the positive and the negative, and you also can use the t multi-graph. So here I show a simple example of a t graph. For example, let's take a let's try to construct a graph which have data points. So here I have defined n equal to 10, and for the each of the data point, let's the value of the x and y is, here I have defined it in a array, and the errors say let's for the each of the data point, let's the error on the x-axis is ex and the error on the y-axis is ey. And here I just take the 20% of the error on the x value for the x-axis for the error on the value on the in the x, and for the error on the values on the y, I have just take the 10% error of the mean value. Now here I have shown the two example of defining a graph. For first, here I have just defined a graph. It's a simple graph where we have only in the x value and the y value, we do not have any error. So we can define it to, like, using t graph like this, where n corresponds to the number of point in the graph, and the x and y corresponds to the value in the x-axis and y-axis for the each data point. Now you can do several other things using the graph, like you can set the marker style for the plotting. You can set the marker color or the data point color, and also put the name on the axes in the x-axis and y-axis and so on. And here I have defined another graph where we have the error on the x and y axis, and the error argument for the error comes after this argument x and y, that is the ex and ey. And if we now run this macro, we can generate can generate the plot for this graph by using just graph draw. And the argument, the argument is the AP. So this A is basically corresponds to the axis and P corresponds to the points. So it will basically produce a graph with the axis that you have defined and with the data point that you have already put some style color. Now you can also put another graph in the same canvas over this graph. For that, you need to do the psame, and remember that if you then do again the AP, then the first graph will be rewrite and you get the axis for only the second graph. So if you want to plot another graph of this graph, you just need to put argument like psame. That means you draw the graph over the previous graph. Now you can see that in the left hand side, in the right hand side, this is the plot that I get when I use TGraph, where we do not have any error, and in the second plot responds to the another graph where we have an error on the x and y axis. Now one can also read the data point if you have access of a T graph, then you can also read the data point from the graph, and it is a little bit different compared to the histogram. In histogram, you can directly get the content or the value of the y-axis of a given bin just by doing the get bin content. But in case of graph, to do it in a different way. For that, you need to define a uh, array or the pointer of a double. That's let's say x value and y value, and you can directly fill this array of this x value and y value just getting the get x and get y. So if you have a access of a graph, like if you have a, and if you do this get x, then uh, all the x values of the data point will be stored in this x file, and if you do the get y, then all the values of the data point, or the y values of the data point will be stored in this y file. Similarly, you can also store the error by doing the get ex and get ey. Now let me go to the function. So the function is very useful in our data analysis, because whenever we have some data distribution, we often need to fit it with some function to get the physical quantity, like mean of the distribution or the width of the distribution or the yield or the area under the curve of the distribution. So one can define the function using the TF1 class. For example, in the left hand side here, I just show a simple code to define a function. For example, here I have defined a function called the signal background here, which have basically 5 arguments. The first argument is basically the name of the function. The second argument is basically the structure of the function. So here one can use the root defined function if you want to. So in the root we have predefined function like Gaussian function. For that you can just write here Gauss G, and for the Poisson you can just write here Poisson. And you can also use the user defined function. So for example, here I have defined this signal background function just above my uh, main code. So you can see here, this is the user defined function signal background, which is basically a sum of a signal part, which is basically a Gaussian function plus a background function. So this Gaussian function, in this Gaussian function, you can directly call this Gaussian function using the T map, where x is basically the x is basically the variable of your function, and this parameter 1 and parameter 2 corresponds to the mean and sigma of your Gaussian function. And there is a third argument, that is the k true. If you in general by default it is k false, that means it do not take account the normalization of the Gaussian, which is basically 1 by root 2 pi into sigma. And if you put the k true, then it will consider the normalization, that is 1 by root 2 pi into sigma. So here is the one of such a user defined function, that is the signal background. And here I have also defined other two functions like signal function and the background function. So you can call this user defined function in your TF1 to uh, get the function that you want to use in your analysis. And the second and third argument is basically the range of the function, means up to which range you want to define your function. For example, here I have defined my function from 0.14 to 0.16. And the last argument is basically the number of parameter of your function. For example, in the signal background function, here we have 5 parameter, like parameter 0, parameter 1, 2, 3, 4. So total there is 5 parameters. Similarly, I have defined another two functions, signal and background. For the signal, we have only the 3 parameters here, and for the background we have only the 2 parameters you can see here. Now for the cosmetic, one can do various kind of cosmetics of the function, like they can use the different style, different line width, different color for the function. For example, here for this first function, signal background, I have set the line style equal to 1. That means it's a continuous line. If you put 2, then you will get a dotted or discontinuous line. So you can do different kind of styling of this function for the draw purpose. And you can also define the width of the function, width of the line of this function, and you can also set the color. Now in the function, you can always set the name of the function. So by default, if you do not set any name, it will give you default value of default name of the parameter. Like for the first parameter, it will give you p0. For the second parameter, it will give you p1. For the third, it will give you p2, and so on. So here for the first function, I have defined the names of the parameter. For the first parameter, I called it as norm or the normal. The second, I called it mean. Third, I called it sigma. And the fourth and 5, I called it background 0 and background 1. Now in you can also fix in your analysis purpose, you can also fix this parameter, or you can also give some initial guess value, or you can set the parameter by using command fixed parameter and set parameter. So using fixed parameter, you can individually fix the value of each parameter, which I have shown here. And if you do the set parameter, then you just give a guess value for each of these parameter. Now one can also if you fit some histogram with some function, and you will have some fit parameters that obtains that is taken by this fit function. After the fitting, you can directly extract those fit parameter by using the get parameter, and you can also extract the error on the fit parameter by using the get parameter errors, which I have shown here. You can store the parameters value and the parameter error value in an array of a parameter, in an array of some double variable. So here, after getting the value from this fsig background, this function, I have again set this in the signal and background, and then I just draw it. And in the right hand side, you can see how these distributions of this function look like. So basically, this distribution is for a fixed set of parameter which is defined here. And this blue line is corresponds to the first function, that is the signal background. This magenta dot corresponds to the second function, which is basically the only signal. And this red dashed line here corresponds to the background distribution, that is the FBG defined in this function. Now another uh, you now another uh, thing another useful thing is to store this root object like one dimensional histogram or two dimensional histogram or THnSparse or function in your root file. So you can do this by using this TFile, which have a extension of .root. So in this root file, you can store any number of root objects that you want to store, and you can define this root file using this TFile, which is shown here. So here I have defined a root file, say fout, and the first argument here is corresponds to the name of the root file, that is the output.root. And the second argument recreate is basically create this new root file with this name. And then you can write any kind of object in this root file, any kind of root object in this root file by using this write command. And you can then close this file using this close command. For example, uh, uh, you can do that, and you can also read the T object from this root file. So here I have given an example how one can read that root object from this T file. So for example, if you have a root file, say input.root, where you have various T object saved, like one dimensional histogram, two dimensional histograms, or so on. So you can directly read those, access those histogram from this root file. For that, you just need to define the a T file pointer, that's the fin, and then you can directly get any of the object of this root file by just using the command get. For that, you need to define a pointer of the object type that you want to get. For example, if I want to get the object which is a one dimensional object, then I just define a th1d h1, and then we can get it just directly putting the name of the one dimensional histogram that you want to access. And here you just remember that whenever you access a object like one dimensional histogram or two dimensional histogram from this root file, and if you want to use those object further in your analysis, then do not close or delete your input file by using, say, this f input close, because when you close your input file, you will lost your lost your object, and you cannot use this object further in your analysis. So whenever after accessing the object, if you want to use it further in your analysis, you don't need to close the root file. Now, after telling about this fit function and t file, let's now go to another important thing, that is the fitting, because in our experimental data analysis we often need to fit any distribution to get some information. So in the right hand side here, I show an example of a fitting. So how this macro works. So we basically we basically have a root file or the T file with this name, which have different kind of T object. So from there, I just define a T file to access this root file. And then from this file F1, I get a one dimensional histogram object that names is F histan like cos for PT1. So that's some name. So this histogram is basically a histogram of a invariant mass distribution. So in the right hand side, in the black marker, you can see that the histogram H1 of the histogram H1 that I get from this file. Now I fitted this histogram with some signal plus background distribution, that is I already defined in my that I already defined when I discussed the T function. So this is the same signal plus background distribution here that I already mentioned in the when I mentioned about this function. Now what I do, I just set the parameter of this histogram, some initial gauge values by using the set parameters. I put some initial gauge values. Now I do the fitting using this. You can always fit a histogram using this fit command, where the first argument is basically the function with which you want to fit, that is the f-sig bg, and the second argument corresponds to the option of the fitting. For example, here I have used three options, that is the ERM. E option is basically corresponds to the error. That means when the function will fit this histogram, it will take account the error on the data point. The R corresponds to the range. That means it will fit the histogram only up to the range that you defined in your fit function. For example, here from 0.14 to 0.16. And aim is the minimization of is basically a algorithm that use the chi-square minimization, and here we have used the minute algorithm that is corresponds to the m value. So if you do that, this histogram will be fitted with this function fsig background. We can see it here in the blue line. Then from this fit function, after doing the fitting, you can directly access the fit parameters using the get parameters and get parameter error. Then if you set or fix this get parameter value in the signal and background distribution individually and draw it, then you can get the signal distribution. You can see the signal distribution. It basically looks like it's basically given shown by this magenta dash line, and the background that is shown by this red dash line. So here the distribution is fitted with the signal plus background. Then the parameter is extracted from this fit function and further used in the other predefined distribution of signal and background to show how the signal contribution and background contribution will look like. Now another important aspect of this fitting is to integrate the fit function to get the contribution from the different fit function. For example, if you integrate the signal distribution here, this magenta distribution, you will get the yield of that particle under this signal distribution. And if you integrate this background distribution under the signal peak, for example, in plus minus 3 sigma from the peak, you will get the contribution from the background. Now one can do this one can get this integral of this fit function by just calling the integral. But in that way in this way, if you want to also calculate the error on the integral, then you cannot do it just directly like a histogram, because in histogram you can calculate the integral and the error on the integral by just calling the integral and integral error. But for the function, you need to do some tricks. So for that, what you need to do here, I put another part of the code. If you look at here, so here I show that how one can calculate the error from the integral of the fit function. So for that, you need to define a object that called the t fit result ptr, and that's here I have defined it with r. Then you can define it r equal to h, and you can just directly fit it. Now what happens here, so in these lines, so if you fit this one-dimensional histogram with this function, it will basically store the parameters and parameter errors, as well as the another thing that's called the covariance matrices, which basically gives the correlation between the parameter in this r value. And you can further and in order to calculate the error of this fit function, you need to use this covariance element of this covariance matrices. Therefore one need to store these elements of the parameters and the covariance matrices, and you can do it by like this. Here you can see I have put another extra comment. For example, this b is not necessary here, and the extra comment that in the fit option you need, that is the s. So this s basically corresponds to the storing of those parameter and the covariant matrix. So if you do not put the S, none of the element of the covariant matrix will store here, and you will not get the correct value from the error calculation. Now, when you do the minimization of the fitting,
Excuse me.
yeah,
Yeah. I just had one small query. So order of this E, R, and B, S, does that matter, or you can
no,
put it
that
in
order does
any?
not matter. You can put it in any order. That doesn't matter.
Okay.
Okay, so when you fit this histogram, in order to calculate the error in a appropriate way, you need also to check the status of the fitting. So this every when you do the fitting, the fit also gives you some status, and every status corresponds to different of meaning. And if you want to calculate a proper error, then you need to check that if your status is 4000. So you can, there are also several type of status that one can check by just looking at the root manual. And I am just mentioning here this the status 4000, which corresponds to a proper calculation of the error. So here I just do a loop and check if the status is 4000 or not. And if the status is 4000, then I just stop the fitting. Now after doing this fitting, you can directly get the fit parameters and fit parameters error by using this get parameters and get parameters errors. Now one also need to get the elements of the covariant matrix, and that is what one can see here in this two line. Here I have stored the elements from the covariance matrices of the fit, which is further used in the error calculation. So for that, you can just define a matrix that mat, and you can get the covariance by just calling the get covariance matrix. Then you can store the uh, covariant matrix of the signal and background in two different metrics. So for here, I have defined two different metrics, that is the mat1 and mat2. And in mat1, here I have stored the covariant matrix of the signal, and in mat2, here I have stored the covariant matrix of the background. So you can see here, if you do the this if you want to store the covariant matrix of a part, you need to just put the parameter number. For example, signal, the parameter is 0, 1, 2, and for the background, the parameter is the background 3, 4, 3, and 4 in the total distribution function, so which is given as input here. Then you can store the covariant matrix in a array of a double number, just get by just calling the get matrix array. So here this B and A, it stores the covariant matrix of the signal and the background respectively, because this mat1 corresponds to the signal and this mat2 corresponds to the background. Now if you want to calculate the error, you can just call the if signal integral error, where you need to pass the parameters with the parameters number, where this n% pad 0 corresponds to the parameters number 0, 1, 2, and then you need to pass the covariant matrix element in that is stored in your a double number, that is the B. By this, you can directly calculate the error on the integral of a distribution of a fit function or of a function. Now, I will talk about the last topic, that is the tree, which is very useful in our data analysis to store the objects and as well as the data. So this tree, it has been designed to support very large collection of root objects, and the usefulness of the tree is that it allows us to access the entry directly and also randomly. Means it can for example, if you have a 100 number of events, and for example in each event you have some event variable called say xyz, and you store this information of each event in the tree, and you can directly access any of that event just you can directly access any of the event by just calling the get entry of the tree. Just here one wants to note that this random access of the tree is less efficient compared to the sequential access. Means if you want to access the tree entry in a sequential manner, means if you want to first get the access for the first entry, then second entry, then third entry in the sequential manner, then that is more fast and efficient compared to the if you want to access it in a random manner. Means if you want to first take the 5, then randomly 10, then randomly 1, in that case the access of the entry is less efficient. Now in this tree, in the main container of the data storage, it can I have already mentioned that it can store any type of basic root objects. And when you store this data, you store it in some several branches. For example, here in I have mentioned that this you can see here this XYZ corresponds to the for example, it corresponds to a 3 event variable. So you can store it in the 3 different branches. And the first branch corresponds to the variable X, the second branch corresponds to the variable Y, and the third branch corresponds to the variable Z. And each of these box corresponds to the event number. For example, this first set of box corresponds to the first event. The second set of box corresponds to the second event. The third set of box corresponds to the third event, and so on. And you can store it in the event by event basis in the tree. Now, how to write a tree. So here I give a small example of writing a tree and store it in a root file. So first here I have defined a root file called tree1.root, and I just create it by using this option recreate. Then I defined a tree using this object TTree by this way, where this T1 corresponds to the name of the tree, and sorry, the T1 corresponds to the name of the name of this object T1, and it's basically the and this a simple it's basically give you the title of the or the name of the tree that is going to show in when you stored in the so when you open this tree, it will basically give you the title. Now, for example, if you want to store 3 variable, for example, if you have px, py, and pz, 3 float variable you want to store, and you want to store one integer variable like say event. First, you need to define the branches for this each of the variable. So you can do it like this way. So you can just define the branch where the first argument corresponds to the name. The second argument corresponds to the also the variable that is you have defined, that is the px, py, pz. And the third argument corresponds to the type of the variable. For example, this px and py and pz are float type. That is why it is defined as /f. And if you want to define a branch of an integer variable, then you need to do the /I. Then when you defined it, you just store the information of this px, py, and pz by just using the fill command that you can use the tfill. For example, here I have just loop over a 1000 track or event, you can say, and I randomly generated observable using this g random number. So this px, and I have randomly generated this px and py. So this ran node is basically return you the 2 number distributed following a Gaussian with mean 0 and sigma 1. And then I define the pz, that is the px square py square, and the event is defined as event is equal to the I. So when you do the tfill for each of these I for or the each of these entries, it will save the px, py, and pz in their corresponding branches. And then you can write the tree in the file that you have defined here. Now you can directly draw or analyze these branches using the TTree draw or the tcut in your root terminal or also in your macro C++ script. For example, here I show how to use this tcut and tdraw to get the distribution of any one of the variable. for example here px or py or pz. So for example, in the root terminal, how we do it, we just define the output root file where we have stored the tree. For example, from the last example, here is the tree1.root is the root file where we have stored this tree t1. So you can just access it. Then you can do .ls, and the .ls will basically show you the content of the file, and you can show there is a tree named as t1. Then you can uh, just give a pointer of your to your tree t1 by just using the TTree, and then and define these as my tree. Then you can draw this any one of these branches of this my tree. For example, if you want to draw the branches that the px, you can just directly do it by this command draw. And you can also do it by using some condition. For example, if you want to draw the px for those py where the py greater than 0, then in the second argument you can put the condition that the py greater than 0. Then it will basically give you the distribution of the px where the corresponding py is greater than 0. Now this condition can also be defined using the t-cut. So for example, you want to define few cuts. Say here I have defined 3T cut like C1, C2, C3. The first cut, you can define it within the T cut. The first cut is basically the PX greater than 0.1. The second cut is basically the PY greater than 0.0. And in third cut, I have just put a AND condition between the C1 and C2. Now you can directly use this cut variable C3 when you drawing this. So if you just draw the PX variable with this cut variable in the second argument, that is the C3, it will basically give you a distribution of px which of this condition px greater than 0.1 and py greater than 0.0. One can directly implement this TTree using this t cut in their C++ macro, and that will make your analysis more faster compared to if you want to access each of the entry one by one. Now, how to read that? Now, in this example, I will show how to read the tree. So here you can see that in the root file that I have shown previously in my example where I have stored the tree. Then in this root file, you can directly access the tree by just doing this get and putting the name of the tree T1. Then you need to set the branches which you want to access. For example, here I have set the branches, set branch access of the variable that I want to access of the tree. That's the branches that are the px, py, pz, and event. If you want to do some faster analysis, for example, if you do not need the branches py and pz, then you can just only access the branches px and event by just it means you can only just access the number of branches that you want. You do not always need to access the branches, all of the branches that is defined in the tree. Then from here, I have just shown how to read the tree. You can just get the entry of the each set of for the each event. Means this, as I mentioned earlier, this px, py, pz is basically I stored it as an event variable. So you can just get the entries for the each of the event by just calling the get entry. Where here I have you can see that here I have put a loop where this loop run from the 0 to n entries. So this n entries is basically the number of entries that is, or the number of events that is stored in your tree, and you can access it by just calling the get entries, and you just loop over it, and for the each of the entries you just access the get entry. If you do it, then you have the value of the px, py, and pz for the ith entry, and you can directly fill it in histogram, one-dimensional or two-dimensional histogram that I've shown here. Then you can just write it in some other output root file. Now here I will talk two more things, and the first thing is the t friend. So it happens several, means it happens often that you have a tree and you want to add some additional branches on some existing tree, or for that one can do it using the tree friend. So how to do it? So here I just put a small example of the tree friend. So here I have shown, here I have just put uh, access a root file where I have a tree called T3. Then I have just accessed this T3 using this get command. Then for example, I have another root file where we have another tree called T3f, and we need to uh, uh, we need to merge these branches of this T3 and T35. Then we can do it by just add friend. For example, in this T3, say we have a variable or the branch called PZ, and which we do not have in this T3f tree, which is stored in this T3f.root. But in this T3f, we have another branch called the that is, say example, the PT. Then we can just if we do the add friend, if we do the add friend of this, this T3, the add friend command, we can just add the branches PT from this T3f into this T3T, and then we can directly access it. For example, here I have shown that in this command basically do that in the T3 tree, you just add the branches of this T35, and then if you draw this T3, for example, if you want to draw the variable pz of this T3, you can draw it by putting a condition on the PT, which is not present in the T3, but which was initially not present in the T3, but you can add it, you just add it using the add friend, and you can do it like this way. Now there is another thing, that is the T forest, that is the forest or the that you can do it using the TChain. For example, if you have a different, if you have various root file, and in the every root file you have the same tree, and you want to merge all the content of this tree and try to analyze it as a single tree, then you can do it using the TChain. So you can just define a TChain like this way, and then you can just add the corresponding root file where you have the tree with the same name and the branches. And if you add them, then you can just use this T as your merge tree, where you have the all the entries from this all these different root files. So it is very useful to merge a large set of root file in your analysis. Now here is another one example to directly convert your dat file or the ASCII file uh, to a tree, and you can directly do it by using the read file. For example, if you have a for example, if you have a dat file called this say basic.dat, where you have three columns, say X, Y, and Z, and you want to convert this dat file to a tree, you can directly do it by just do t read file, where you need to first define this tree T, then you can just call this read file, then it will basically read this dat file and convert it in a tree where you have a three different branches, say X, Y, and Z. So you can directly convert that file to a tree. Now I will end this first lecture with another example of reading this tree. So you can, I have shown that you can read the tree by just setting the branch address here in this example. You can also do, so root also provide you to do it without doing this set branch address. You can directly do it by just calling the make class. So this make class command will basically create a reading macro and a class to read your tree. For example, here I have a root file. If you just open it in the root terminal, then if you just do the ls, you will get the corresponding or t object that is saved in this root file. For example, here I have a tree in this root file that is called the t1. Then if you do the t1 make class, and in argument if you put some name, say reading, then it will produce a two file. That is, one is the reading.h. In this header file you have a class that corresponds to the different branches of the tree, and using this reading.c you can directly read those different branches for each of the entries of the tree using this reading.c. So it's very easier to create a reading macro of some unknown tree, that if you have some unknown tree, then you can directly create a reading macro using this MakeClass command. So today I will stop here. So I will give some basic idea about the root, and the next following days I will mainly focus on the analysis part. In that, basically I will show how to analysis task from scratch in the LA physics framework, and how to submit job, how to debug your code, and all those things. So thanks for your attention. Is there any question?
Hello, sir. Can I ask one question?
Yes, please.
Can you show me a slide before this 20, slide number 20? Okay, I just want to see how it is done. Okay,
Slide 20.
yeah, I just want to see. Okay, there was another slide on fitting where you told that the status should be equal to 4,000.
In fitting here,
Yeah, fitting.
how to do the error calculation?
Yeah. This error calculation using fit function. I don't know about the status. What does it mean? What does it make sure of?
Okay, so if you means the status are means well defined in the root guidelines. What number is this corresponds? For example, this 4,000 it corresponds means when you do the root fitting using the minute, using the chi-square minimization, you will get different kind of status, and the status for example 1,000, 2,000, 4,000, etc. This 4,000 corresponds to a status where this minute algorithm calculate the best possible covariance matrix for your appropriate error. Means this error is depends on the covariance matrix elements. So it will basically calculate the best possible or the best set of covariant matrix for the.
Okay. So if I don't define this
So if you
statement,
okay, if you don't find this statement, then your fit.
I don't use this statement, but I don't expect a good fit.
Yeah. So the thing is that if you do not get this 4,000 status, if you can find status 1,000, in that case, you will have a good fit, you will have the good chi-square minimization, but your error on the parameter would not be appropriate.
Okay.
That can happen if you limit your parameters. For example, if you limit your some fit parameters, and if your parameter reaches the limit, then you will get the best fit of the chi-square minimization, but that will not propagate to your error. That will give you some wrong error.
Because I remember earlier in the root version, the fitting was not very confidential. The confidence level was not very good, because you see that the fitting is very good, but you don't get the good chi-square value. So for
Yes,
that, I think
that chi-square value depends on various things, like on the amount of your error on the data point and which algorithm you used. So here the status, I just want to mean that the status that corresponds to the accuracy of the error calculation of your error calculation.
Okay, so to make sure that you have a good accuracy over the chi-square, we should use this particular statement on the status.
Yeah, means if
And
you want
status.
to calculate the error from the fit function itself, then you
Hmm.
need to check this status.
Okay. Thank you.
Hello. Hello.
Yes, please.
Yeah, this is Pratyay from Bosch Institute. So I have a question in this slide actually. So in the bottom, you have shown that you take this T matrix D sim mat,
Yeah.
which will take basically R get covariance matrix. And in the next line, you wrote that for the signal, you will use this 0 and 2, and for the background 3 and 4. So these values, are these values fixed, or they
No.
depend on something?
Okay, so here if you will look at the first line, here you get the covariant matrix of R from R. So what
Yes.
is R? R is basically store the covariant matrix from the fitting where you use the fit function F signal background. So in
Yes.
the F signal background, you have 5 parameters.
Okay.
For the first 3 parameter is the signal parameter and the last 2 parameter is the background parameter.
Okay, so it
If you
depends
want,
on that.
yeah, it depends on that.
Okay, thank you.
Yeah, Saurabh, there is a question in the chat box from Saurabh Goyal. So he is asking whether there is an upper limit in the number of branches we can make in a tree.
Yeah, there is some upper limit. I do not remember it now, yeah, but there is some. It depends on the memory allocation. So there is some. I do not remember it now.
Hello, sir. I am Sachin.
Yeah.
So let's say we have created a tree and we have set all of its branches and we saved it in form of some root file. So can we make another code in which we can add some additional branches to that pre-existing tree in that?
I showed that you can use it using the TFriend.
Yeah, but in the case of TFriend, we needed some additional root file, and then after we added branches to it, and later in the code we used our conditions to extract that specific object, or we need to draw it.
Yeah, you need to have another branches in some another root file or another tree. Then you can.
So I'm asking that we cannot add directly from that. Let's say here it is, let's say T3.root has 5 branches, so we cannot write another code in which we can open up this root file and add some additional branches to it.
I think no, means I do not know if it can be done.
Okay.
Means you are saying that you just open this tree and you want to add another arbitrary branches of your one.
Yeah.
I don't think it is possible. I tried once. It was not easy. There was no way actually. TFriend was the best possible, but that doesn't solve the problem many a time.
Actually, this tree is basically designed for just only the storing and reading. I mean, so it is difficult to do those kind of modification.
Okay. Thank you.
So looks like there are no more questions. So thanks, Saurabh, for these nice presentations. Many new things you discussed. So it's not only the trivial things, so it is very good. I guess everyone who attended must be getting benefited. So I think this has been a long day today. So is there anything from the participants you want to say something?
Thank you, Siddharth. But the slide